Greenhouse hydroponic crops use many fertilizers, and aquaculture needs wild forage fish for feeding fish. Both hydroponics and aquaculture produce a huge amount of wastewater. How can we combine fish and hydroponic production, in a circular economy perspective, to reduce their impact on the environment? Easy. With SIMTAP. SIMTAP is standing for Self-Sufficient Integrated Multi-Trophic Aquaponic System. In the SIMTAP, commercial feed is replaced by worms and shellfish, which are reared in the system to clean the wastewater from fish tanks. The plants and microbial community are also responsible for the maintenance of water quality suitable for fish. To provide fish with enough feed, worms and shellfish are fed microalgae, cultured in photobioreactors with greenhouse wastewater. This is how greenhouse crops can be linked to aquaculture. Plants and fish are both products for food market. SIMTAP is a marine aquaponic system. Hence, halophytic plants are grown, for instance salicornia, a gourmet vegetable. Therefore, the SIMTAP is a closed system that reduces the environmental impact caused by greenhouse crops and inland fish farming. Simple like SIMTAP.
The project officially started in June 2019. However, the activities were significantly delayed in 2020 due to the pandemic caused by COVID-19. Therefore, in agreement with Prima, we decided to ask for an extension of the project, which will terminate on May 2023. So we are halfway through the project. However, I think that the results achieved so far are quite interesting. We installed the 4 prototypes in France, Italy, Turkey, and very recently in Malta. In Malta, the system did not yet host any test, while several experiments, especially on fish feeding, were carried out in France, Italy, and Turkey in 2020 and this year.
The SIMTAP system, conceived by INRAE and the Lycée de la Mer in Bourg-Sofran in France, is based on the integration of sea bream, oyster, clam and kuruma shrimp in a closed water loop in other ponds. Those ponds are used by people there to grow or to refine oysters in this area of Marais Noliro. We chose to feed the sea bream only with vegetable resources in formulated feed, which is completed with discarded mussel from producers in the area. By this, we expect to have a better sustainable feed for the fish. The effluent from the fish produce naturally phytoplankton, which is reused by the oysters and clams in the pond downstream, while the kuruma shrimp valorize the organic matter directly and indirectly by eating the small invertebrates which develop inside the ponds. After the first year of experiment, the proof of concept was confirmed, which means that we had very good growth of each species, fish, shrimp, and oysters and clams. We had very high levels of survival in the oysters and good levels for clams and shrimps. The flesh yield in the shellfish were very high also. Therefore, we think that we produce here a new kind of system which is robust and we hope permit to produce food of good quality in a sustainable way by integrating all these complementary species which have also a good market price. Another experiment is running actually in 2021, and we expect to have good results also this year.
SIMTAP system at the University of Pisa is an integrated multi-trophic aquaponic system and consists of 4 main units. The main unit is for fish rearing tanks. Then we have the detritivore filter feeder organisms unit, and we have the bacteria unit, and then we have the macroalgae and plant unit. So the SIMTAP was designed according to the environmental condition we can expect inside the greenhouse. The water circulates from the fish rearing tanks to the detritivore filter feeder organisms. So the suspended solid can settle down in benefit of the filter feeders and detritivore organisms. The dissolved substances in the solution, mainly ammonia nitrogen, pass through this section and reach the bacteria unit, where the nitrifying bacteria transform the ammonia nitrogen into nitrite and then nitrate. Within the autotrophic unit, the nitrates are absorbed by macroalgae and plants. So they purify the water that can be recirculated and reused within the system itself. Therefore, the accumulation of toxic substances and the water discharged by the system are minimized, reducing the overall water consumption of the system. Gilthead sea bream is one of the most important species reared in the Mediterranean area. It can live both in marine water, of course, and in brackish water. For this reason, SIMTAP system can take advantage of low salinity water, up like 25 grams per liter, to better grow plants within the system itself. In the ongoing experiments, we tested the enhanced inclusion of some detritivore and filter feeding organisms into the diet of fish. Those organisms can be reared in the system, so they can reduce the diet components such as fish oil and fish meal. The experiments were conducted at a density within the fish tanks from 5 up to 15 kilos per cubic meter. And results show that including up to 40% of mussel in fish diet can increase the growth of fish compared to a commercial feed. On the contrary, a reduction of around 10% in terms of final body weight was observed when commercial feed was completely replaced by a mixture of mussels, clams and polychaete worms on a dry whey diet basis. So in our system we tested several species of the detritivore and filter feeder organisms. The best ones were the polychaete worms such as Ediste diversicolor and oysters. The mussels and holoturia, instead, they didn't perform so well. Talking about Ediste diversicolor worms, we captured some wild individuals and we put in the system in February. After 4 months, we observed a 3-fold increment in density. Up to now, we reached 5,000 individuals per square meters. That is around 2 kilos of fresh biomass of polychaetes. So the experiment conducted in Pisa focused on 4 halophytic plants: purslane, sea beet, salicornia and atriplex. The salicornia is also known as glasswort. Another plant tested was a salinity-resistant glycophytic plant that is a Swiss chard. All the plants were grown hydroponically at a salinity of 25 grams per liter. Swiss chard and glasswort seem the most suitable plants, respectively grown during autumn-winter season and spring-summer season. Glass is a very interesting crop because in spring-summer it can produce up to 4-6 kilos per square meter of fresh shoots in 2-3 months. In Italy, glasswort is considered a gourmet vegetable, so it can reach a quite remarkable market price, up to 10 euros per fresh kilo. This price is close to the price of farmed sea fish, like sea bass and sea bream. The SIMTAP system installed in Pisa includes some photobioreactors for the cultivation of algae on wastewater from greenhouse crops. These waters are no longer suitable for greenhouse crops, in particular due to the high salinity, but they are still rich in nutrients and thus can be used as a growth medium for the cultivation of algae, for the production of biomass, for feeding the tritivore and filter feeder organisms. Moreover, the photobioreactors are sources of a low salinity water free of nitrates and phosphates. The water can be used to compensate the water losses due to evapotranspiration from the aquaponic system. In a recent experiment, we found that a strain of ubiquitous alga Chlorella vulgaris can be grown on a nutrient medium consisting of runoff water from hydroponic greenhouse tomato culture. However, the biomass production was lower compared to the growth found on a standard growth medium.
The University of Bologna participates in the SIMTAP project with its Biosystems Engineering Group based at the Department of Agriculture and Food Sciences of the University of Bologna. Our interdisciplinary team has been focusing on the design and development of an integrated smart monitoring and control system supporting the SIMTAP plants and in assessing and optimizing the energy consumption in the SIMTAP installations. At this stage, the integrated smart monitoring and control system has been designed, tested and implemented in different SIMTAP pilot plants. It has been delivered specifically for this project, benefiting of the expertise of our group in this field, spanning and mixing various research fields and approaches: design, modeling and monitoring of smart and agri-food structures, smart farming and precision livestock farming, energy modeling, and machine learning and big data. We all know that smart monitoring and control systems can help increasing efficient management of the agri-food sector, contributing to support and provide evidence for food safety and traceability, sustainability, and animal welfare, all topics of which consumers are increasingly aware. The SIMTAP system must rely on a balance among the modules of the system, their various species and the surrounding environment, and are being tested in order to work in different environmental conditions and production cycle configurations. This calls for continuous and precise monitoring of the several metrics, thus for a specific system taking care of that, and it must be flexible, scalable and open. Our challenge has been to deliver an integrated system within each plant, among different matrices and domains, air, water and energy, and among different plants in different geographic regions. An integrated smart monitoring and control system has been specifically designed for the SIMTAP plants with the aim of allowing monitoring of environmental data and energy consumption, the creation of a time series of collected data, and real-time remote control and increased operation accuracy. Our system has been implemented in the indoor SIMTAP facility at the University of Pisa. It's a protected environment where most parameters are controlled and need real-time monitoring across air and water in combination with outdoor conditions. Our system is also running at the French SIMTAP plant in completely different conditions. In fact, our system is both integrated and suitable both for SIMTAP inside buildings or structures and outdoor facilities distributed over wide areas, like in the open ponds of the Lycée de la Mer in the Littoral. The data stream generated by the system can allow to increase the system reliability, providing support to everyday functioning and preventing system failures like oxygen, high and low temperature, etc., and to provide data for research. Tracking crop and plant growth conditions is useful to analyze production performance. And tracking energy consumption is allowing both the sustainability assessment and energy optimization. We do believe that besides supporting the development and test of the pilot SIMTAP plants during the project, our monitoring system will support the application in future commercial exploitation of the system. And that's why we are facing now a new challenge. We are now working to develop a multi-criteria spatial analysis model that will be implemented in a geographic information system. The goal is to deliver a decision support system that can facilitate the implementation of SIMTAP plans in different Mediterranean contexts.
The major inspiration source for the SIMTAP prototype in Turkey was the sustainability of unmanned marine hatcheries, with a special interest in the extreme conditions of the Mediterranean, including high air and water temperatures and high salinity. For this purpose, the studies were mainly focused on test a low-cost prototype for European sea bass and gilted sea bream hatcheries and a possibility of utilization for a full growth period. The prototype was mainly composed of a fish culture unit, a ragworm culture unit, a hydroponic unit, a microalgae culture unit, and a series of water recycling and conditioning equipment. The first results showed that the SIMTAP system was highly similar to a traditional flow-through system in terms of specific growth rate in European sea bass and gilted sea bream. On the other hand, the recent experiments revealed valuable results on the inclusion of ragworm meal in place of fish meal in point of weight gain and health indicators. The experiences encourage us. The SIMTAP system highly close to maximum yield for fish, halophyte plants, microalgae and polychaetes, as well as zero or minimum waste discharge.